Let me welcome you to the 33rd lecture of the drilling and blasting technology course, and in this lecture we will start our blasting result part, where we will try to evaluate our different blasting result to understand the performance of a blast. But like every class, what we do, let us retrospect what we have learned so far on this. So far we, in our previous lecture, we discussed about the objective of the blasting, which is carried out in the surface and underground cases, and it is carried out, blasting is carried out for mining and civil industries, and the objectives are different in both the cases. We have also studied the different types of blast design and their procedure and their procedural steps, so that the design can be made to achieve the desired result from a blasting. So, the important part is that the result is important, which is essentially required for which the blasting is being carried out. So, the blasting result is very important. In fact, the objective of our present lecture is basically to understand the blasting results. So, objective of this class, which will continue in the next few classes also, is basically to analyze the blasting results, so that we can evaluate the performance of a blast. And as we have discussed, what are the objectives? Our objectives are to fragmentation, our objectives are to economic blast, our objective is also to reduce the ill effects to the environment and to achieve the desired safety in the total blasting process. So, our primary objective to achieve the desired fragmentation, and the desired fragmentation must be achieved with the laid down economic constant, and while we are doing this, achieving fragmentation within the limited cost, we should not give much impact on the environment, and the total procedure should not be unsafe, it should be safe enough. So, this is the requirement of a blast, and our objective is to essentially evaluate these performances, so that we can analyze whether our blasting is good or not. So, like every class, we generally start with a video. So, let us observe this video, in which you can observe a very good blasting initially in a real time frame, then it will be shown to you in a slower pace, so that you can understand how the blasting is carried out here. So, this is basically, this blast is basically categorized as a very good blast. If you look into this, this is the phase, this is the real time blasting is carried out. There is absolutely no stemming ejection, mark profile is very good, fragmentation is very good. If you see it in the slower pace, in between we will stop it for a while. Say, let us stop the video at this position, and you can see there is no stemming ejection, there is no flame come out from the mouth of the holes, the movement of the rock is very fine. You can see the fragmented rocks are of very good fragmentation, smaller size fragmented rocks are there, and if you see, the throw is also very good, there is no fly rock generated from the blast, or fugitive particle is not going out of the blast. So, that means the overall performance of this blast may be considered as a good blast. So, that is why this high speed photography is a tool where we can get a very good picture of the blast, and you can understand that this blast is may be considered as a good blast. And by this way we will understand how we will evaluate different performance of different blast. And let us see what are the parameters we need to analyze to check whether our blasting is good or not. And our first parameter is called powder factor. This is also called charge factor or specific charge, which basically nothing but an economic factor which dictates the economy of a blast, where it is expressed the tonnage of material excavated per kg of explosive consumption. That means, it is an economic term, and obviously, there is no term used here for the type of or the grade of fragmentation. So, that means, the powder factor will be evaluated only when the fragmentation is in the satisfactory position. In that case only powder factor is evaluated, and it is basically giving us the economic term of a blast, whether the more cost is required for the blasting or less cost is required, that economic analysis may be carried out from this powder factor. Next one is the fragmentation. Fragmentation is basically the size of the blasted material. In fact, when we will discuss it in this class at a later stage, we will understand this fragmentation is basically the size of the boulder formed from a blast, and obviously, there will be a heterogeneous distribution of these sizes, and there may be few particles of very finer sizes, there may be few particles of very large sizes, and there are other particles which are in between the large and the finer sizes. So, this fragmentation of the rock is basically the fragment size distribution of the boulders which are formed in the blasting. So, this fragmentation analysis is very important. In fact, this fragmentation is the prime objective of a blast, because we want to fragment the rock mass into a smaller sizes, and this size of these requirements are different depending on our different use of the fragmented rock. It may be a larger, where we want that lump size should be required in our plant or something like that. It must be finer, where the mineral has to be liberated from the ore. So, all those cases are considered when we are considering the fragment size distribution. So, basically this is the economic term, this is the desired result which we want, and this all are the other terms. This is the safety one, and these are the environmental considerations. So, fly rock is basically the rock which is ejected from the blast site unwantedly, unwillingly, and you can say it is a fugitive rock particle which is moving out, and that may hit anyone, maybe human being, maybe the cattle, maybe the structures, and may create damage or the injuries or the death of the person or the cattle. So, this is a very important one, considering the safety of the blast, performance of the blast, and this noise which is basically generated because of the air overpressure, that the shock wave generated moving through the air, the noise is generated. So, this is the unwanted sound which is important, which is generated, should not annoy the nearby resident. Next one is the ground vibration, which create the vibration of the ground, that may damage the nearby structures, that may create annoyance to the flora and fauna, and that is why these two are very important environmental parameter that needs to be taken care of during the blasting. So, basically these are the performance one must consider while they are discussing the blasting process or evaluate the performance of a blast. So, let us start with our few more parameters are there. This is one very important, considering the effect on the remaining rock mass, that is how much damage is occurred to the remaining rock mass. One is called over excavation, another is considered as the cracked formation in the remaining rock mass, that may result into the destabilization of the area, and that is another important point often considered especially in case of civil engineering, where the structures are built by the rock excavation blasting, should have an large or very high life, expected life, and that is why the stability is very important. In those conditions, this parameter may become very important. So, these are some of the performances which need to be considered during the evaluation of the blast performance. So, now for the first, let us consider the first parameter, which is nothing but the powder factor. This is also called charge factor, also called specific charge, and this is basically a direct relationship which gives us the idea that how much explosive is required to blast a certain amount of rock. So, basically this is expressed in the tonnage of rock produced per kg of explosive. Some cases it is also expressed in terms of that meter cube of rock produced per kg of explosive, or in the reverse way it may be expressed that the kg of explosive required to excavate 1 meter cube of rock. So, whatever it is, basically the idea is same. The idea is that it is basically dictating the economics of the blast. So, basically it is giving us the idea about the economics of the blast, and this is also dependent on the fragmentation. That means, if we are giving less amount of charge, that means less amount of shock wave is being generated, which basically fragmenting the rock in a larger fragment size. So, if we are using less amount of explosive, then the fragmentation achieved is a coarser fragmentation, and that is why that may gives us some different powder factor term, which is giving us basically deviating us from our target. So, this powder factor, specific charge or charge factor, these terms are important only when the fragmentation achieved are satisfactory. Basically, it has been observed that the powder factor is having a curve like this, where this is gives us the optimum point. That means, the fragmentation is not satisfactory in this position also, fragmentation is not satisfactory in this position also, and in this position the charge amount will become the satisfactory and we achieve the optimum fragmentation in this case. So, that is why this fragmentation is very important, and it is having a relationship, indirect relationship with the powder factor. So, powder factor must be considered or must be calculated only on that case where the fragmentation achieved is of our satisfaction, and in that case only we will calculate the powder factor. Generally, what we do, theoretically we consider the powder factor is nothing but the tonnage of blasted material per kg of explosive. Designed powder factor is another term. Designed powder factor is another term which is considered as tonnage of material is nothing but the burden into spacing into bench height, that is giving us the meter cube of material. It may be converted to tonnage using the specific gravity of the rock material, dividing it by the explosive charged in that particular hole. So, basically it is considered if this is the hole and this is the burden, then up to this explosives are placed. So, that explosive quantity placed here expressed here and the material excavated is considered this one, which is having if you are looking at to the plan view, having an influential area of this, which is nothing but the S by 2 at this side, S by 2 at this side. So, this is nothing but an S spacing distance. So, basically that is why the total volume of material excavated by blasting this hole is burden into spacing into bench height, dividing it by the charge placed in that hole may be considered as the designed powder factor for that particular blasting. However, actual powder factor may little bit deviate from this designed powder factor, because in blasting over excavation, which we have already discussed in our previous slide, or under excavation may occur. So, our actual achieving powder factor may be differed from the designed powder factor. So, that is also another important part one should consider. Dyno Nobel and Smith in 1951, they have given some idea about the powder factors expressed in kg per meter cube, that means in charge factor for low strength rock, very low strength rock, medium strength rock, high strength rock. So, their powder factor they are finding out in terms of this, where low strength, high strength are expressed up to 1 to 100 MPa, and for the greater than 100 MPa this may continue, and you can see this is in the increasing order, this is in the increasing order. So, that means this will increase 0.8 kg per meter cube of charge quantity requirement for the more stronger rock. However, with changing of the explosive, with changing of the explosive loading system, this may powder factor may also influenced by those properties which has to be taken care of. The next part, next influencing parameter is fragmentation, which is basically our prime objective. The prime objective of the blasting is basically the fragmentation, and the main and most important result of a blasting is its fragment size. Rock fragment size directly affects the cost of drilling, blasting, loading, secondary blasting and crushing. A fragmentation process is said to be optimum when the oversized boulders are minimum, ultra fine productions are minimum, lump sizes are maximum, and it is fragmentation enough to ensure that efficient digging and loading by the excavator or excavating machine, and muck pile must be loose enough so that the bucket can be filled very fast, and that is why very good performance of the excavator or performance of the shovel can be achieved. So, a fragmentation is basically give us an idea from this. So, if you ask one very experienced miner whether this blast performance is good or not, without any measurement taken out by the different measuring techniques which we will discuss, a person may say fragmentation is good only looking at these 5 points. So, if the person, experienced person is looking at this 5 point, observing that the oversized boulders are generated are less numbers, in general it is considered if it is less than 5%, then it may be considered as a good blast. Ultra fines generation are also less because the airborne fines are less, lump size are very good, uniform fragment size are observed, and shovel can perform better on this. Mark profile is also very good for the performance of the shovel. So, considering this, an experienced person may tell that this fragmentation is very good, but where is the measure of this fragmentation? You can see these are the sizes of different boulders. These are the sizes of different boulders, and it is essentially required that one should know the size of individual boulder while he is trying to assess the fragmentation. So, basically the technique of measuring this is to analyze the size of the each and every boulder, so that an average size distribution may be achieved from this. We will discuss this in the next slide also. So, this measurement of fragmentation can be carried out by visually, which I have already discussed. An experienced person can tell this fragmentation is good by observing the fragment size from the top. The best way to achieve the most accurate fragment size distribution can be achieved from the sieve analysis, while if different size of sieves are placed and the amount of material which is retaining on each screen we will analyze, and finally, we try to achieve the fragment size distribution in between the screen sizes. So, this is very important, and this basically gives us the most accurate, this is the best method of analyzing the fragmentation. However, the problem is while we are having bigger size boulders like 1 meter cube or 1.5 meter cube size boulders, placing those boulders on a sieve or go for analyzing the sieve analysis, having that big size of sieve, then the mechanical power is required to shake that sieve, all those criticalities are there, and it is almost practically impossible to carry out sieve analysis for a blasted mark profile, blasted mark. So, blasted fragmented rock mark cannot be sieved by the sieve analysis. So, that is why though it is the best, but practically carrying out this exercise is almost very impossible. So, that is why we discard this sieve analysis in most of the blasting cases. Another estimation like visual size estimation which is carried out is the loading production rate, that is another indirect method from which we can understand whether our fragmentation is good or not. The most commonly used method is basically digital image processing. In last slide we have seen the last slide we have seen this is basically the photographs of the fragmented rock mass. So, basically in our digital image processing we take this type of photographs and we go for analyzing these photographs through image analysis technique, which is now presently available, in the electronic world. So, basically we go for image analysis of these photographs through different softwares, and what this software do? They try to trace out the edges from these images and they consider the equivalent area which are created by these edges. So, basically this is the most commonly used method today to quantify the fragmentation, so that we can get the mean fragment size which is called K50, and also the distribution of the size. Say this is the material which is basically, this is the cumulative mass, this is the size, and say this is the 50%. So, this is basically the average fragment size. However, there may be another distribution possible like this, where average size distribution is same, average size is same, but the distribution is different. So, the most of the boulders achieved are in this range, that means from this range to this range, whereas here the distribution range is little bit wider. So, not only the mean fragment size is important, fragment size distribution is also important, and that is why nowadays the K20 and K80 is also important, and the line joining this K20 and K80 is basically considered as the measure of fragment size distribution. So, that is why not only the mean fragment size is important, but also the fragment size distribution is also very important while we are analyzing the fragment size. So, this is the first model which are given by the Kuznetsov to get the mean fragment size, and this depends on the rock factor, the volume of rock broken, and the explosive charge quantity required equivalent to TNT. So, this is the first model which is given by the Kuznetsov. So, this Kuznetsov model was given in 1973, and later on in 1983 the most popular model was given by the Rosen-Ramler, where R is the proportion of material, he has expressed in terms of an exponential function. R is the proportion of material which may be written on size x screen using these two empirical constants and this one, these two constant, they found this is exponential, it is an exponential function. And if the R is considered as the 50%, then the value achieved by this x is considered that value of x is considered as the K50 size. So, for R is equal to 50%, the value of x achieved is basically the K50. So, this Rosen-Ramler equation is basically designed, to get the fragment size distribution, which we have discussed in the last slide, distribution which is very important. So, that is why this is very important. This n, the constant n is basically not actually constant, this is called uniformity index, which basically govern the slope of that K20 and K80, and that uniformity index may be estimated as a function of burden, hold dia, standard deviation of drilling accuracy, spacing by burden ratio, charge length, bench height, like this. These are the influential parameters for the uniformity index. These are some other estimations for uniformity index. This is the modification of the Kuznetsov model, where different formula are given. Now presently there are n number of softwares available for fragmentation analysis, WIFRAG, split, portametrics, and in India CIMFR has designed this Fragalist software. So, we will look into this software a little bit at this position. So, this Fragalist 4 is basically evaluating the same way the fragment size distribution. This is the step 1, where the figure have to be uploaded, then the uploaded figure the scale has to be calibrated. For calibrating the scale, these two corner points must be selected, so that the scale along the x axis, scale along the y axis may be fixed by the software. Then the threshold parameters of sigma value has to be given, so that the edge detection techniques can be easily followed with the contrast in the image. Then the edge will be automatically selected. Every time it is user has a given facility, because automatically the edges may not be created detected properly. So, the user has the option to manually select the edges using the cursor in the software, so that it can be accurately selected. And after selecting this one, the equivalent area under this, as the scale is already given there, the equivalent area under this is computed by the software. So, by this way the area is considered and the size is calculated from that area. Then the size distribution curve is prepared, from where the D50 this D50, this D50, then this is D20 K20, and this is K80 can be K80, 1 minute, let me clear it again. This is the D20 K20, this is the K50, and this is the K80 may be achieved from this size distribution curve. So, this is the Fragalis software. The principle is same for the WIFRAG also. Let us observe this video of WIFRAG. You can see the photograph is taken in the mine. Then the photograph is loaded and the fragmented rock picture is there. This is the scale. So, the scale is selected, the scale is given. Now, the edge detection is carried out by automatically by the software, and then the fragment size distribution curve is made. So, the basic principle is more or less similar. The different techniques are used for the edge detection. The accuracy of these softwares depends on the edge detection technique carried out. So, nowadays with the modern edge detection techniques, the softwares perform very well in most of the cases, and it also depends on the type of material also. So, basically this is the method we carry out for the fragmentation analysis. I expect that you carry out more reading on different blasting from different blasting books, especially SME handbook, then the books of Jimeno, then the books of Professor Bhandari. So, you can carry out more reading from those books, and let us stop this lecture at this position. We will continue this lecture in the next class also with the other with the evaluation of the other parameters. Thank you.